to the cloud. So welcome back. I just need a bit of coffee and then we can get started. Still too hot, so I'd better get started and then come back to the coffee subject later. This is where we were yesterday. I remind you of the larger context, which is bifurcation theory. Big subject, you know, it used to be whole conferences on it. There's still whole sessions about that. Clearly, the reason is that because it deals with something very important. It deals with some qualitative changes under varying parameters in a system. Those can be quite spectacular, unexpected, dramatic. So a lot of the scientific phenomena are, in fact, bifurcations that we wonder about. I'll talk about those a little bit when we get into specific bifurcations. Important to realize that bifurcations happen near points where the system is not robust. So if we talk about bifurcations of fixed points, you cannot have a bifurcation from a hyperbolic fixed point because hyperbolic fixed points are robust. They are just, you think of their eigenvalue configurations, they're separated from the imaginary axis. So if you tinker with them slightly, you can get them perhaps closer to the imaginary axis, but fundamentally the system will have the exact same topological type. So whenever you hear the word bifurcation, there has to be some sort of critical parameter value. There has to be a critical parameter setting in which the subject whose bifurcation you're considering takes place, the subject itself develops momentarily a neutral stability type. And that's true not just for the bifurcation of fixed points, but for the bifurcation of periodic orbits or limit cycles, bifurcations of any invariant set in general. As long as the invariant set as a whole has stable directions only, or unstable directions only, or a mixture of stable and unstable directions, it will not bifurcate. It might deform, it might move, but fundamentally will not change, right? Qualitatively, because sudden qualitative changes are always related to a change in stability, always some eigenvalues when you have a finite dimensional system for sure, crossing the imaginary axis or being on the imaginary axis. So that's where bifurcations take place. So there are qualitative changes, and basically we define local bifurcations as occurrences at some fixed point and at some parameter value mu naught, such that such that the system is no longer topologically conjugate. The system at criticality is no longer topologically equivalent to all nearby systems. So it's a local notion. We restricted attention to bifurcation of fixed points. We do have a fixed point. That's the assumption at some critical parameter value. And we talk about a bifurcation in general if nearby, not all nearby systems, nearby in terms of the parameter, okay, are topologically equivalent to what you had at criticality. And this big picture, I find, this is what I always have in mind when I think about bifurcations, is this, in the space of dynamical systems, there are these critical surfaces. If you cross them with a parameterized family of dynamical systems, again, one point in such a curve or such a surface in a dynamical system, that's where a bifurcation takes place. Because what these surfaces do, they separate different topological equivalence classes, and near the crossing point, arbitrarily close to the crossing point, you will see members of one class and the other class as well. So it is no longer true at those points that a whole neighborhood of this point along the family would have the same topological type or equivalence class. So that's sort of the big picture. You could have models that are not appropriate for really discovering all phenomena that can happen, that actually turn back right there. So you want to make sure that your model is not like this. And I gave you an example where this, instead of a general mu parameter, which can change its sign and therefore would lead to what we call the pitchfork bifurcation without even, just informally, without even studying it in detail. So you would not see the whole thing, but rather you would be just confined to seeing this branch of the story. Then you would turn back once you hit zero, because this would not take you this regime, given that the parameter that plays the role of mu is confined to negative values, even as you change a from -infinity to +infinity. One note was the idea of universal unfoldings, which means suppose you diagnose that your system is here. What number of parameters should you then start varying in your system that you may have actually fixed for some reason because you thought that those were just design parameters that you don't want to touch because somebody told you that the object looks good if you pick those parameters. How many of those should you unfreeze and perhaps allow them to vary so that you discover all possible phenomena in the system, okay? And universal unfolding would be a parameterized family of systems that's locally able to see all possible equivalence classes. And if two such bifurcation surfaces intersect, then a single parameter, or at least a low dimensional surface, because, you know, I'm trying to draw in an infinite dimensional phase space. So nothing is what it seems to be. By this surface, I don't necessarily mean a two-dimensional surface. I actually mean generally a Codimension-one surface, which means it has one less dimension. So it's still infinite dimensional, but it has one more because the space of dynamical system is infinite dimensional, but it's able to locally kind of divide the space, right? So nothing in dimension-wise, nothing is what it seems in my figures, but conceptually these are okay. So this doesn't have enough dimensions, this curve type crossing at that point, because there's 1, 2, 3, 4 local equivalence classes, and this one only explores 2. So if I take another point along that, you know, high degeneracy, which lies at the intersection of two bifurcation surfaces, then pictorially, I just showed that I need a larger dimensional surface so that when I move along this surface, I will see all possible occurrences. So this bifurcation would have a higher dimensional universal unfolding. And again, it's think of these as families of dynamical systems. This is a high dimensional family than this, which is simply, it doesn't mean that you change the dimension of the vector field that defines the dynamical system. That actually remains the same. What you change is the number of free parameters that you unfreeze and you don't consider constant. Number of parameters that you use to detune yourself from criticality, okay? And the codimension of a bifurcation, I can put an A here, is the minimal number of parameters that you need. Because why unfreeze 50 parameters if you get away with just varying 2? Because already the 2 get you in all local equivalence classes, then why create more problems for yourself? So that's why it's a valuable notion. Any questions on these so far? I hope I have been able to fix the audio. I actually tried everything. I've spent about an hour after the class. I even asked people to call me and talk to me, and nothing worked. I checked, then, you know, the good old solution when all fails, do a restart. So I restarted my computer, and sure enough, it did work. At least when I called myself, it did work. So actually, would somebody mind speaking up just for a second if I hear it? What they say? Ahmed, would you mind just saying something?
Yes. Hi, Professor. Can
I
you hear
still
me?
can't hear you. So that's a mystery, right?
Can you hear me? Can other people hear me?
What this is. Then I called myself really yesterday, and I heard it. Then I'm sorry. Then this is a particular case in which even the restart didn't fix things. I'm not sure what's happening. I checked all within the preferences, within Zoom, everything looks fine. Did a restart? Okay. So what it means that please, however inconvenient that is, I'm just going to be paying attention to the chat. And if you have any questions, just chat. Sorry about that. Okay, so let's go to then what I wanted to talk about, specific bifurcations. And that means that people have done the homework and they looked at specific bifurcations. They worked out, you know, what they went through the whole machinery. They identified the center manifold for these types of systems. They looked at the normal form of the system on the center manifold, which, remember, is a tool that enables you to simplify the dynamics as much as possible. And then they looked at what point you can cut that normal form so that the truncated normal form, in fact, is topologically equivalent to the full system on the center manifold. And they also looked at that once you do all that and the critical parameter value, how many parameters do you have to unfreeze then to be able to see all nearby things. So this work has been done, at least for the most important low codimension cases. You could increase the complexity, the degree of degeneracy of systems endlessly and just look at higher and higher codimension bifurcations. And that was actually fashionable for a while. But I think the most important ones are the ones that don't have such super degeneracies, right? Because those multiple degeneracies, I mean, when you are in a figure like this, right, it means that two things are simultaneously going wrong in your system, in the sense of it being atypical. To be at a bifurcation point, that's already atypical, because why would you be exactly there, right? So you can be all over the place, right? Why would you be exactly there? But there are systems that, especially, that when you change parameters, that you will be there, but there will be certain symmetries and everything. So each and every one of those special features of the system adds another layer of degeneracy and another layer of unlikeliness. So there's no reason really to write a book on codimension 5 or codimension 6 or codimension 10 bifurcations, because they're highly unlikely. There was a reason to study codimension-one bifurcations and even some of the codimension-2 bifurcations. What I'm going to do here in this class is give you a quick overview of codimension-one bifurcations. So these are bifurcations in which already one unfolding parameter suffices so that you see everything nearby. So this is codimension-one bifurcations of fixed points. In the books that I referenced at the beginning of the class, there's some really good treatments of this subject, especially Guggenheimer Holmes does a great job, because they give you all the they don't give you all the technical details that you don't need, but they give you insight. So I will just mention that here, that see Guggenheimer and Holmes that is not to be mistaken for George Howard, right? The GH. This is that would be without a dash. That's Guggenheimer Holmes. But you can also see me for more detail, sure. But I think this is a fantastic book to have. I always say, if you wanted to own just one book in dynamical systems, I would recommend this book still. So all these years. So Guggenheimer Holmes for more detail. And in fact, for some higher codimension bifurcations as well, not just codimension-one. So what's the simplest setting in which you will have a bifurcation? Well, what's the simplest setting to have eigenvalues on the imaginary axis? Well, just have a single zero eigenvalue, right? So let's look at that. Which means it's an unrepeated zero, right? If you have a repeated zero, that's actually where the codimension-2 case. So the setting is that, just to set that up, we have some dynamical system which is multidimensional. It has a right-hand side that also depends on parameters. So y is your phase space variable, n-dimensional, and mu is a p-dimensional parameter vector. Okay, and the assumption that we're going to make is that whatever critical parameter value leads to the zero eigenvalue for this system, I'll just shift the parameter. So that's the critical parameter value. Once again, this can be a high dimensional parameter vector, but it turns out in the end, it's enough to pick one. Now, but it has to be the right one, because you may have a parameter whose impact on the system is not meaningful from the point of view of the bifurcation. So it doesn't, I have an n-dimensional parameter vector, but maybe the way I've chosen it, even though I'm varying those parameters, and even though one parameter variation would be enough to get me through the bifurcation, and I would see everything, it doesn't immediately mean that the parameters I have there originally are filling that role. Because think of this A here, right? This will turn out to be a codimension-one bifurcation that you see here, right? And this system has, at zero value of that parameter, a single zero eigenvalue because it's a one-dimensional system. And from the start, I have a parameter in it. Now, is that parameter, and this will turn out to be a codimension-one bifurcation, is that parameter then automatically qualifying for being as the bifurcation parameter? No, because the way it's positioned in the system, it's that the unfolding it provides is not a universal unfolding, right? So just because you have a parameter, it doesn't mean it's a good parameter. But people said that people have looked into that, and then they say, okay, whatever you have originally, you will be able to then find another one. Maybe one component of this parameter vector is good, but maybe not. But ultimately, there will be one that you can use a single one, because I'm classifying it under codimension-one, so that you can use to unfold that. Okay. Now in that case, the result of that, the universal unfolding, I'm sorry, I haven't yet stated the setting. This is a multidimensional system. I have to state the setting. So first of all, I want to say that we have a fixed point at 0, right? So when I plug in y equals 0 and I plug in mu equals 0, which is my critical parameter value, then I get 0, which means that the right-hand side vanishes there, right? So that means we have a fixed point at 0. So that's one of the assumptions. And the second assumption is that if I attempt a linear stability analysis at that point, so I take the Jacobian of the right-hand side with respect to my dynamical variable y, right? And then I plug in y equals 0 at the critical parameter value, which is mu equals 0, then the resulting Jacobian will have the property that the dimension of its center subspace is 1, right? So that will actually imply that there will be a one-dimensional center manifold. So the dimension of the center manifold attached to 0 is 1. And the eigenvalue configuration that I'm looking at, all this happens, keep this in mind, it's part of my assumptions, that if this is the real part of lambda I, and this is the imaginary part of lambda I, and this is a multidimensional system, so generally speaking, I'll have lots of eigenvalues on both sides, in fact, of the imaginary axis, right? And may have repeated ones here and there, but there will be a single one sitting at 0, and it's real. And there's no other eigenvalue on the imaginary axis, okay? Only that single one. That's why I have a one-dimensional center subspace, and then I know by center manifold theory, since all the others are separated, that there's a one-dimensional center manifold, which is tangent to that subspace, okay? So that's my initial setup. Then I get to the points that people have done their homework over the years. And it turns out that a universal unfolding for this case is the following. It's fairly simple. On the one-dimensional center manifold, you can find a coordinate. I call it x because I may have had to change coordinates a number of times using normal form theory to get to this. So x dot equals, and the way this looks like, there will be a one-dimensional parameter mu dot. It might just actually be, one component of this one, or maybe mu was initially just one-dimensional, and it might work for this. I don't know that. One needs to check that, whether that parameter, when you actually go to the center manifold and do the normalization, whether that parameter actually plays this role. So the system has to have a constant dependence on it. And then either plus or minus here x squared. And I need to explain that a little bit, but this is it's either of the two. And this is already simplified to the extent possible. You either have the plus sign or in a given system or the minus sign. So here, and I'll explain that in a second. Here, importantly, now x is just one-dimensional, and because it's a codimension-one bifurcation, as it turns out, mu is also one-dimensional. Okay. The fact that it's a codimension-one bifurcation is perhaps not so surprising. The reason being that I have a fixed point somewhere that's by itself not a degeneracy, that's a starting point. And I have a single degeneracy here because a single eigenvalue is on the imaginary axis. It turns out that if you have multiple, the more you have here, the more unlikely is that what I'm drawing will happen to you. And that means that the more surfaces, bifurcation surfaces that you show here will intersect at you, okay? But right now, I only assumed a single one, all right? So it's believable that you're just basically residing at one point of a single surface like that, okay? But once again, any of your parameters that you may have might just do this to you. That's why I'm not using the original parameter. You may have to redefine your parameter to be mu tilde to actually cross that surface, right? And that particular thing just depends on a given problem. Then why are we doing this to begin with, if I can only come up with that in a given problem? To give you an idea of what will generically happen when you diagnose this for your system. You do linear stability analysis, you do this, and then what this will give you is an idea that, okay, in the absence of any other funny business about my system, any symmetry or degeneracy, what can I expect? And it's exactly what you can expect, what this little system gives you. The other question is this plus minus. Why is there a plus minus? Your original model would not have a plus minus. And what decides whether it's a plus or minus? Well, the way that plus minus comes in is that people wanted to have the simplest form, kind of bare to the bone form for this normal form. And therefore, they did one more step than they would normally have. And what was originally, what you would have after, reduction to center manifold, to the center manifold, and then passing to a truncated normal form, and adding an unfolding parameter. I'm just unfolding parameter. And at this point, I just call that unfolding parameter that you're adding, say, delta, okay? Right? Because you did all this analysis then, and you conclude that delta is it's a single parameter is what you need. And what you would originally have is something like x dot equals delta plus some constant that depends on your system times x squared plus, higher order terms. But again, already this one captures the system behavior. So if you just want qualitative understanding, the good news is that people have determined that this already captures everything you have, because for small values of delta, this system will be topologically equivalent to the full system. But there's no sign of plus minus here. And also there's no 1 here, as I claimed, but there's some A here, right? And the system must be truly nonlinear for this to work. So no more degeneracies, remember. So A is non-zero. Then to kind of clean things up and make them more universal in terms of conclusions, one can just rescale time. So we introduce new time. And that time can just be for rescaling time, that can just be the following tau, okay? And I'm just going to say A absolute value times t. And I take the absolute value of A because I don't want to reverse time. I just want to stretch time, but not, if A is negative, then time would be reversed. Then all the arrows on my trajectories would be reversed, and I don't want that, okay? So when you do that rescaling of time, then remember that if you take the time derivative of anything with respect to t, that's just going to be, by the chain rule, you take that the time derivative with respect to tau, and then you take the time derivative of tau with respect to t. But if you differentiate tau with respect to t, then you simply get this A absolute value, right? And then you perhaps see what I'm getting at. Well, I didn't leave myself enough space here for that, but I'm practically done. I'm just rescaling time in this general equation that I had here, okay? So x dot, based on this, just becomes A norm x prime, where prime is the prime is d by d tau, okay? And that equals delta plus ax squared plus blah, 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 because I only rescaled time. I didn't do anything to the variables. So if I then express x prime, then it gives me delta over A in norm plus and potentially minus 1, because depending on what the sign of A was, A divided by A norm works out to be either +1 or -1, right? And it will just depend on the given problem. If A was positive, then I will get +1 at this point. If A was negative, I get -1 at this point, right? That's why you get this. Okay, and that's the reason. You kind of see, so you don't have to necessarily do this, but in a given system, you might, if you're interested in the dynamics, you would do some sort of central manifold reduction. You don't have to repeat that this will be your normal form. You will have to do a little bit of work to make sure that you transform out the linear terms. Note that we only have a constant term, and there's no linear term in X. So this enables you to transform out the linear terms, but the quadratic terms have to stay at criticality, and they will have some sign. Okay, so that's where that, so this is kind of an aside here. That's where that plus or minus is coming from. All right, so it's one of the two, but the beautiful thing is that this is it. So this already captures, you have a curved manifold, okay, on which who knows exactly what happens. And on that, you have a full dynamical system, which is described by a polynomial. But the good news is it's enough just to look at the leading order term, because near the origin, this already captures what may happen, okay? And now, what is that may happen? Let's see. Well, this system is easy to analyze because it's one-dimensional. So what we do, I'll just do the analysis for the minus case. The plus case is very similar. So what we do in this business is bifurcation diagrams, as I mentioned. They are not difficult to draw in this case because you have a single parameter mu tilde. And remember that as a function of mu tilde, I can actually plot full phase spaces for full phase space dynamics because they're all one-dimensional. Well, that's an interesting effect there. Okay, I was able to tilt the phase space. So for each value of mu tilde, I have something. So what you see here is now the bifurcation diagram. So when mu tilde, remember I fixed this negative sign here. So when I have mu tilde negative, then nothing happened. I have no fixed point because this is then a negative number. So x dot x just keeps decreasing. So in these little phase spaces, you have just decreased. First, when you're away, this adds to your decrease. So you're fast. This also adds well, that is irrelevant along this line, sorry. So your decrease is sort of larger, right? You get closer, the decrease decays. And then finally, right there, you don't have a decrease. Sorry, that is not correct. What you have is not coming from mu anymore, but it's coming from minus x squared. And that doesn't give you a linear decay anymore. It gives you an algebraic decay because it's coming from a quadratic term rather than a linear term. But it's nevertheless a decay. Except that right at that point, because mu is 0, since this term is out, this is all you have, right, in the equation. Now you have a fixed point at x equals 0. So let's mark that right here. Except that then that shouldn't be the axis, and the x equals x-axis should be here, because that's 0. Mu equals 0. Okay, so now you have a fixed point. And then when you start, again, still remember that I have a negative sign here. Now you move to positive territory with mu prime, then you get 2 fixed points, because all of a sudden you can solve the equation for 0. So you get x equals plus minus square root mu tilde being positive. This gives you 2 roots, and they open up as a square root function, and it's negative. So as you do, I'm already using if you do a stability analysis on them, I'll indicate what you'll get. So you open up for 101, and the upper one will be stable, and the lower one will be unstable. One quick way of seeing that stability, then what you would need to do is not that that's complicated, then you would have to then linearize the system at these equilibrium points, right? This branch is just x naught equals square root mu tilde, and this branch is x naught equals minus square root mu tilde. It's not hard to linearize there. But one thing that sort of a quick trick is that if x is large, because it has a negative sign, then it doesn't matter what mu does near 0. For large x values, this minus x squared will clearly overpower mu. I'm thinking with mu near the origin. So when I go out, further out, then this decay in the x will not change. So that means for large enough values, I will clearly have to decay. And also the same is true actually for any large absolute value of x. So when I move out further in this direction, right, then this term over the minus x squared overpowers the other term. So for sure, I also have to, for large values, decay. Okay. So then this already gives you an idea that in between, perhaps more generically, that I will do this, right? Of course, I could still be doing this, but that would mean that, look at this fixed point. This would be a non-hyperbolic fixed point, because in one direction it attracts and the other direction it repels. And this would also be non-hyperbolic, because it in one direction it attracts, in another one repels. In one dimension, along one line, you can only do that if it has a 0 eigenvalue and the repulsion and attraction is coming from the nonlinears. That's unlikely. But you can convince yourself that these are really hyperbolic fixed points by simply doing a linearization at these points, plugging in and get an eigenvalue, right? And then I leave that to you. So they will be non-degenerate hyperbolic fixed points, all these. So the upper one is therefore stable, and the lower one is unstable. This is unstable. I'll just explain the colors once, and I will always use the red for unstable and the blue for stable. Okay, so this is what happens in all these systems. So it doesn't matter how many dimensions you had. These are the assumptions that are enough that if nothing else, there's no other degeneracies in the system, then immediately, without doing any analysis, you will be able to make the following prediction. My large system, potentially 1 million degrees of freedom, do a quick linear analysis, just look at the spectrum of the linear part. I find that there's only 1 0 there. And you will know for sure that if you move generically your parameters, then on one side of that critical parameter value, you will see no equilibrium for the system. which means that the one that you're working with will disappear. And on the other side, you will see, you will have two. You will see one. You will see one, which is here. And you will not see the other one because it's unstable. But the other one will be from one side be acting as the boundary of your domain of attraction. Okay, and that will be its role. Because if you then pass that, this is the one you will be seeing, right? Nothing, and all of a sudden an equilibrium is born. And interestingly, one hallmark of this type of bifurcation, which we have already called, right, fold bifurcation. I already gave a name to it. Except that when we analyzed this in a given problem, it was unclear at that point that this is such a general phenomenon that you would in fact generically see it whenever the spectrum of the linear part like this. So anyway, what you see for that system is that no equilibrium on one side, all of a sudden an equilibrium is created, and that equilibrium will actually grow then fairly rapid. It will move fairly rapidly, right? As you change your parameter. Look at the slope here. Just really rapidly for a while, okay? That's one hallmark, a physical observation of the fold bifurcation or saddle node bifurcation. And the other thing is that there will be a ghost equilibrium point. I say ghost because it's unstable, you don't see it, but it will limit the domain of attraction of your new fixed point. So from one direction, I say here from above, but you know, in your parameter space, who knows what that direction is, somewhere along the center subspace, right? From one direction, you will have a pretty comfortable stability margin, but in the other direction, you will have a more limited domain of attraction. And if you perturb your system more in that direction, then you will actually be seeing also growth. You have to be careful in one direction, not so careful in the other direction. But as you tune your system away more from criticality, even that direction will develop a more sizable domain of attraction. So this is the physical phenomenon that you will see, and it's enough to predict this based on a linear analysis. So you need to do linear analysis, identify that this is the case, and then you can say, you know, generically, if all my parameters are generic parameters, so they do have an impact in the system, then this is the phenomenon that will occur. So I expect then a fold or saddle node bifurcation. Now, this is an incredibly important bifurcation, and you can guess, right? Because the reason you guess is, okay, the more a bifurcation will be more prevalent if it doesn't assume really any additional degeneracy, because many degeneracies, many things going wrong at the same time is more unlikely. One thing going wrong at one time is likely, right? So in a parameterized family, this is more likely to happen than this, right? That because this would mean that I'm in a situation where several things are going on at the same time. So therefore you expect, okay, this should be the most prevalent bifurcation that I should actually be seeing all the time, but you may not necessarily recognize it. But let me give you one prevalent phenomenon, which is actually explainable by this bifurcation. And that's the phenomenon that you may have heard in really different areas of science, is hysteresis. Except that I misspelled. So an informal definition of hysteresis could be that the dependence of the system output, and I think I found that somewhere, I don't remember where, but the dependence of the output depends on past input. And you see that in electric circles, and often people then say, well, then the system has memory, right? So I have to then use more complicated modeling, because apparently what I'm doing right now doesn't just depend on where I am in the parameter and the phase space, or it also depends on my history. And then you can model that in fairly complicated ways, have an integral over the history, have delays and everything. And those are no longer ordinary differential equations. Those are functional differential equations. And then you might get pretty complicated stuff. It turns out you don't necessarily have to do that. So the generic phenomenon of you may have seen this that people or systems behave differently under uploading and downloading, and the loading would be, measured by some sort of parameter. So suppose you have some parameter in the system mu, and you have some characteristic amplitude that you measure in the system for steady state. Okay, and this is some sort of loading parameter. Then you would find that you have a particular history during while you increase that loading parameter. So for instance, you could find a history like that. Okay, and then you would see a jump at the critical point of mu, and then you would continue like this. And you would wonder about that jump, but you would say, okay, something catastrophic happens there. So the steady state was moving continually. Okay, and it was deforming, and all of a sudden, whoo, that was a big one. And you would not even really resolve this. This is what you see in experiments and in numerical simulations. Excuse me. Very often in books or papers or in any material, people just connect that with a single line. But don't take that serious, because if you really can connect it with a single line, what that would mean is that you have a fixed point here, you have a fixed point there. That's not the case. That's not what anybody observes, right? So the single line, a solid line, I find a bit misleading, because it would suggest, well, a solid line here, or equilibrium, so you have all these equilibria here, right? Coexisting. No, by no means. What you actually have is this was your last point in the experiment, and the next point is here, because you have some finite resolution in the experiment. Okay. Okay, so there's one surprise, but the biggest surprise comes, in fact, when you say, you know what, I'm really curious what happened here. Maybe I had, while I'm adding, why don't I just go back to that point and see, maybe I can get a better reading. So then you start unloading. So you start moving backwards. And what I mean to say is that you're spot on, you're just moving along the same curve. I mean, in an actual experiment, there will be a difference. It will never be the same, but you will be very close, okay? Because why? Because there's measurement errors, there's noise, but fundamentally you will be spot on, okay? And then you say, all right, so now I fully expect maybe a better resolution of this jump. Maybe it was just really a very steep curve. Okay, so I'm coming back, and I'm going to be more careful, and I will use smaller steps. And then to your amazement, instead of then having a well-resolved steep curve there, your unloading experiment knows nothing about this, and it just keeps going. And there's actually not even any steepness involved there. I didn't mean to, it was incorrect to suggest. So I just want to draw it like this, that you continue like this, which is a major puzzle, right? And then you start developing the same type of thing that you've seen here before. And then unexpectedly you jump again, even though when you did the uploading, you didn't jump at all. And then you go to this and continue there. So this is a classic example of what people call with hysteresis, by the name of hysteresis. And by the way, it happens a lot, for instance, in force-damped vibrations of mechanical systems, even fluid mechanical systems. In that case, however, it's a bit more general than what I have described here, because here I've been talking about fixed points. Each and every point here was a fixed point, okay? When you measure vibrations, everything is moving. You don't see a fixed point, but you will see, say, maximal amplitudes, okay? And you can record them. So what these would be, steady state, I'll add that, for instance, maximal amplitude of a vibration, or mean amplitude. Let's just And the reason why that still falls in this category, you could say, oh, this is just hand waving, right? Because he's trying to match bifurcations of equilibrium to vibration. How is that? Well, it turns out that the exact same bifurcation theory also applies to maps and discrete dynamical systems. And when you have a steady state vibration, you can just take a stroboscopic map. It's called the Poincare map of the system with the period of the vibration. And then for that discrete dynamical system, any point on that sustained vibration, constant amplitude, periodic order will be a fixed point. So in that case, you just take the whole theory of bifurcations, and instead of applying it to continuous dynamical systems, as I'm doing it now, you would apply it to maps. The only difference will be that when you start working in map land, the critical case of the zero eigenvalue would turn out to be the critical case in map land is having a 1 eigenvalue. Okay, +1, because for maps, not doing anything means having an eigenvalue 1, because you're not flowing points, but it would be x equals y. You're not, or xn plus 1 equals xn. You're not going anywhere. You take the Jacobian of the right-hand side. You go not going anywhere means having a 1 eigenvalue rather than 0. Anyway, there's an analogous theory of bifurcation theory, center manifold, centers, everything for maps, but the critical sort of dividing line for map in map land is not the imaginary axis, but the unit circle of the complex plane. Okay, so just keeping that in mind, if you see vibrations, then you can take stroboscopic maps of those vibrations and talk about the Poincare map that maps a given point in the vibration to the vibration 1 period later. And when you have a steady state, then that point becomes a fixed point for the system. Okay, so these are the fixed points for an appropriate stroboscopic map. So, and then I say, then the response curve is the set of fixed points for a stroboscopic map. So that's why what I'm saying here is relevant. Okay, so think of these as fixed points for the map rather than for the dynamical system. How does this picture explain that? The two don't seem to be related at all, to be honest. Well, here's the thing. Let's just at least use the right colors to get some intuition. First of all, I didn't use the right color because I just wanted to describe the sweep. So you know what? I tried to change this color to this, because when I use blue, that suggests a stability type, and I went in. Of course, the fact that I'm observing it means that it was stable, but I want to make a distinction between what's really there and what I'm observing. So let's just say this. I was on the way that up in mu, I was steadily observing this branch. What does that mean? It means it had to be a stable state, because there's always little errors and measurement inaccuracies, external noise, whatever in the experiment. If I observe a steady state, it's not a question. It has to be stable in an experiment. Otherwise, I wouldn't be observing it, because there's always imperfections there. So with confidence, I can assign a blue color to this branch, okay, up until here. And then the same happened here, that I was observing this part of the branch actually twice. So it was stable, but in fact, this branch was reaching over here until it curled up. I was observing it, so it had to be stable. So here's the thing that explains this picture, that I fill in the rest with a different color, this. So that's exactly what happens here, that at these points, although very often the experiments are not detailed enough to resolve, but there will be actually, this curve is blowing up in terms of developing a slope, which is infinitely large. The same here. So it will have a slope that's infinitely large. And what happens in these systems is there are two saddle node bifurcations. There's one here, and there's one there. So then what there is in between, which is something I never observed, but it's still there, is an unstable response curve. Okay. And the reason why I don't, and that explains the experiment, because I was proceeding, you know, it's quasi-static an experiment. So as I change, you know, I stop mu, and then I let the system stabilize. Then I change mu, then the system catches up and stabilizes again. Now, what happens at this point? I actually lose the stable equilibrium point. So when I move slightly from that point, I still have a vibration that's going on here because the system has been operating, but I have changed the parameter. That means locally there's no more stable equilibrium. So what used to be a stable vibration is all of a sudden is just a general initial condition and looks around and goes with the flow, right? So that general initial condition all of a sudden is looking for stability. So it's just going to be heading in this direction and then stabilizes here. And then I move, then that's quasi-static fashion always restabilizes. So this is what I observe. Now what happens on a downsweep? What happens on a downsweep is the opposite. It didn't matter how I started where I started the system. It finds the stable state and stabilizes there, produces me a vibration. I change the parameter slowly. It will upset the system because that state is no longer in equilibrium, but it will restabilize, and that'll go on, right? And at this point, my system knows nothing about that point because it's too far away, right? So it always, quasi-statically, I change the parameter, so it will always look for the nearest equilibrium and settle down there. And that story, therefore, goes on up until this point. At this point, in this direction, I wipe out stable states for my system. So when I increase this mu or decrease further, all of a sudden, this is just a generic initial condition. There's no nearby equilibrium point. It starts wandering. So it jumps here to the stable one, restabilizes again, goes on. Okay, so that's the explanation. So you see how incredibly important this one is, even though I don't observe it as a stable equilibrium point. Okay, but it's a demarcation line between the two. It's also interesting that suppose you're here, okay, and you have stabilized. Now you go there, you grab a hammer, and you hit your system. So the forcing you don't change. You don't change the forcing. Say this is some oscillating machine part, and it's subject to some forcing and damping that doesn't change. But all of a sudden, let's not be as violent with a hammer. Just you basically accidentally you push your apparatus. By doing so, you're actually displacing the system from its current equilibrium point. Now, if that push is minor, you come back, okay? But there will be a critical push over which you actually unexpectedly jump to the other branch. So that's another interesting phenomenon in these systems, that they're pretty resilient to perturbations. It has some steady state vibration. But boy, if your perturbation reaches a finite site, all of a sudden you go to a completely different state. And that is something that has received a lot of attention these days, because that's the idea of a tipping point. And people even talk about that in the context of climate change. So just imagine that this can be the current state. And in fact, the model, don't just imagine, this is what the climate models show, that you're basically operating near a point like this. Okay. And there can be perturbations to that, and either call this one the tipping point, but because there's some change in the parameter that in the climate. And for a while, that there's a slight change in the climate, right? But you still restabilize, and the new sort of set of parameters. What people are afraid of is that will come to an end, and at some point you just jump to a different climate. And that can be, say, an ice age, right? Fairly quickly, right? So a sort of fashionable term for this these days is tipping point. And it's fashionable for an alarming reason, because It's hard to go to a conference in applied math these days that doesn't talk about that doesn't have at least one session or several talks devoted to tipping points. You could say, well, if it's so well understood, then that we're done. No, because it's all about the models, right? How do you exactly model climate? These are hugely complicated models, and a lot of their components are not well understood, such as one of the things, as I understand, is cloud modeling, because so much depends on how the cloud dynamics is actually modeled. So that is where really the main advance is to be expected. But in terms of the phenomenon, we have little low dimensional models that show that possibility already. And the little low dimensional models are very relevant. It turns out that's what bifurcation does, because they are related to large dimensional systems like this, right? In a it's a very rigorous fashion, right? This is what happens on the center manifold, right? Now, in case you don't recognize this, those of us working in, or those of you working in mechanical vibrations in practice, this is what you see in experiments in which people talk about hardening springs or hardening nonlinearities. Just need a thicker line. So in mechanical systems, say you have hardening. Springs or hardening or softening. There's two different phenomena. So you have some hardening nonlinearity in the system, and you do in mechanical systems that loading parameters, so to speak, that what plays the role of that. I'm going to show both cases here. Is the frequency of the forcing, some periodic forcing that people use to test a shaker frequency. That very often that's how you test the integrity or the current state, or for instance, could be even in principle an airplane wing or any solid structure whose structural integrity or structural condition you would like to interrogate at this point. Those parameters change for a system over its lifetime. So there are vibration professionals who test that. So in that case, this would be a forcing amplitude. Sorry, frequency. And what a vibration professional would measure is the response amplitude. Again, response amplitude. Because the two different cases I want to look at is the hardening nonlinearity or softening nonlinearity. That can be the mean amplitude of a periodic response that you observe after a while, after your system settled for that particular forcing frequency, or either the mean amplitude or the maximal amplitude. It's probably the mean amplitude. Maximal is easier to measure. And a linear, if I do the same for a linear system, I should show that here for reference, which is a spring which has no hardening effects for its springs. It's a linear spring. Then the same, I'll just show the linear case. Linear spring. This is something we tend to learn in dynamics classes and ODE classes, second order oscillators with forcing and damping, right? Periodic forcing and damping. So if you, I think in when I taught dynamics, we call it a magnification diagram or response diagram, a force response curve of FRC, that is for forced response curve. And it's a classic curve for linear systems. It picks up, for the static case, and it reaches a peak in resonance. When you're resonant with the natural frequency of the spring, it goes down, okay? And this is This is the resonant frequency. And the force response amplitude curve, the amplitude divided by the forcing. And this is just response amplitude. Sorry, I'm just abbreviating things, but I'm explaining them. This is the response amplitude divided by the amplitude of the forcing. And if everything else is constant in the system, this turns out to be the same curve always. So if you don't tinker with the damping, then if you change the forcing, then of course you will have a larger response. But if you then always normalize the response by the forcing amplitude, that turns out to collapse the same curve for a given value of damping. However, if you change the damping, then what will happen is that this curve will be the oscillations will be mitigated more. And then first they come down, become smaller and smaller. Peak is always in the same location. Finally, barely anything. And when you have really huge damping, then you just go down like that. So this is increasing damping. Importantly, there's this line, right, which serves as the peak of these, and that doesn't change. Fundamentally, it's always at the resonance. You always get the largest response at the resonance. Now that's resonance. Now, a nonlinear system, nonlinear oscillators, still just think about a single degree of freedom, will also have a resonant frequency, which comes out from its linearization. So when you substitute a nonlinear oscillator with its linearized spring, so to speak, then certainly there will be a resonant frequency there as well. But two things will happen, is that if you fix the damping, then different forcing values will result in different curves, even when you normalize the response amplitude by the forcing. So for a fixed damping value, you're not going to get this universal curve. Okay, your response will depend on the forcing amplitude. There will be no linear input-output relationship between the response amplitude and the forcing amplitude, because the system is simply nonlinear. So there will be a dependence on the forcing in addition to a dependence on the damping. So in fact, people then tend to fix the damping because in a given system, the damping is fixed. It's a given system. But when you interrogate that system with different forcing levels, then the response will produce different curves. Had you done that in the linear case, you would be always getting the same curve had you fixed damping. So here, fixed damping. Because changing damping in a given, you can't do that experiment. Well, if you have an involved experimental setup in which you can, you change the damping by putting in additional dashpots or whatever, increasing the surface roughness in the same experiment, of course. But normally, if it's the same structure, then this is sort of more of an academic exercise and just tells you how the curve changes. Fixing the damping in the experiments is very reasonable. It's the same structure, but different forcing levels. And what you will find is that for small amplitudes, you will be close to the linear one. So it's almost like a linear. It would be very close to a scaled linear response. But as you start increasing the amplitude, forcing out, then the response starts going in the hardening case in this direction. And this when you see this experimentally, this is the hallmark of a hardening spring. Except that you will never see this in an experiment. Even in numerics, you will have a hard time seeing it. The reason is that this is a theoretical curve that shows you how the response amplitude, there will be responses of that amplitude, but it's only the stable parts of this that you will be observing, like these. So whenever you actually see a turn, you will lose observability because there will be a fold bifurcation there. So if I just want to work on these, this is a theoretical diagram that, because I wanted to just show how it relates to the linear case. So what you will actually observe is up until this point, until it starts turning back, you see it. And from this point, when it turns again, you see it, but in between, you won't see it because it's unstable. So you will have these fold bifurcations all the time. And that's why when you do vibration experiments, you will be able to map this out. Your vibrations settle down. And always, invariably, in nonlinear systems, you will see a jump. And you move on. Okay, you will not see that in a linear system because this curve is never multiple valued over the frequency. In a linear system, for a given forcing frequency, you always see one response. Sorry, I wasn't paying attention to the chat. I go back to that question now. Does the whole notion of universal unfolding bifurcation hysteresis and also carry over to non-autonomous systems, as for the example of the forced oscillator? That's a very good question. So this discussion that I have here is for autonomous differential equations. Now you said all of a sudden, how do I brought in the forcing? That's clearly a non-autonomous differential equation. There's none of this surprise. You're absolutely right. The way it still applies, I pass to maps. And when the forcing, the system is non-autonomous, but periodic, then there is a well-defined discrete dynamical system, which is always the same map, taking me from this point to one period later. So that's an autonomous map, okay? For a general non-autonomous dynamical system, which has general time dependence, I'm not able to craft such a map that would be autonomously always giving me the same evolution from 0 to capital T, from capital T to capital 2T. And so it would be a non-autonomous map because the forcing is all over the place. But for time periodically forced dynamical systems, there's an equivalent formulation for them in terms of autonomous maps. And autonomous maps have this type of bifurcation theory. That's why it applies, okay? So I wouldn't say it carries over just stochastically forced dynamical systems in this sense, but certainly for periodically. It also turns out that some of this also carries over to quasi-periodically forced dynamical systems. It's a bit of a more step up. But again, in all these cases, you're able to associate an autonomous map with the system one way or another. In the case of quasi-periodically forced one with several frequencies, you actually have to fit another map. You will be sampling multiple frequencies, so it will not be just a simple one-dimensional map. But there is an autonomous formulation. That's an excellent point because you might be wondering how I'm bringing in autonomous dynamical systems. I'm relying on the theory carrying over to autonomous maps, discrete maps. Okay, so then I could now go back now and at least for yet another one, I meticulously do this again. So this is the part you would observe, okay, in an experiment. And this is the part you would observe. And when the experimentalist would tell you that mysteriously things have jumped, then be aware that this is exactly what happened. Fold bifurcations right there. And the experimentalist would see the hysteresis and report it. So, this would be the upload cycle in terms of, they call this upsweep, frequency upsweep. And you would be going, and then you jump here, right here, and you continue. Okay, and in the other direction, your jump will be at some other point. So this will be the down sweep. You would jump here and then keep moving downwards along the same branch. So this is seen all the time. And at some point that will disappear. And that's the point where you actually lose the overhang. Because for small forcing amplitudes, so I should note then what these different curves are. So here, the different curves represent increasing forcing amplitude. So that's what distinguishes this curve from that. Okay, but at low amplitudes, you're essentially linear, which means that qualitatively, in fact, you're topologically equivalent to a linear system there in domain. And the way to see that is that really that for one particular forcing frequency, you just get one response. There's no overhang. But at some point, you will start developing an overhang. And the minute you have developed an overhang, you can no longer describe this dynamics by a linear system. It's then a nonlinear system. And just for completeness, I add that here as well. And this will be just, I can just say that near linear response it's not identically linear, right? There will be already a small deformation. You take a bump and deform it, but there's still no overhang. But at some point you will develop that. Now, I spent a lot of time on that. The softening, the sign of a softening spring is just the opposite. That you're for small forcing amplitudes, you may see a bump here, but as you start increasing the forcing amplitudes, you start seeing the overhang in the other direction. Except again, I mean, this is a pretty bad drawing, but perhaps you get the idea. There's a well-defined curve for the peaks of these, so to speak, right? And that curve actually emanates from the resonant frequency. Okay, so what's true again here, without me completing the whole diagram, is that you now have an overhang, but in the other direction. And again, only parts of these will you be able to observe here up to the bifurcation point. Maybe I'll just show one of them. So this is a softening spring, depending on where you go. Okay. So these are very, and you don't just see them in mechanical, and you see them in testing electric circuits, you see them in fluid mechanical, fluid structure interaction problems. These are universal diagrams. Just know what's behind them, okay? Always the simultaneous existence of saddle node bifurcations, and you will only observe the stable branches, and you will have multiple stable branches, say for this frequency. This is 1, and this is 2, but in between there's an unstable one, and that calls the shots in terms of domains of attraction. Okay, if you're here, but you're applying a large enough perturbation to this otherwise stable state, you may then actually, in the same experiment for the same frequency, you will start seeing the other one. So even when you're doing a normal downsweep, and you would just always see this branch, even if somebody kicks your downsweep experiment, it may actually get you over this and red curve, and then you will start seeing the other one as well, kind of out of the blue, right? Okay, that would be, I said a lot about, so I just wanted to tell you that the saddle node, no wonder that it's so important. No wonder that it's so important, I wanted to say, because that's the least amount of degenerates that you have. And again, this physical example shows us that bifurcations are rare to begin with, right? Because in this general point, there's no bifurcation. But when they happen, they will almost inevitably happen in a parametrized family of systems. The parametrized family, the parameter here is the forcing frequency, right? Okay. And I will just say, because this was an excellent question about non-autonomous systems, that all the above can be explained by fold bifurcations applied to the stroboscopic or period T mapping as a discrete dynamical system. Associated with the system because in that context, when you have a period T orbit, for the continuous dynamical system, okay, it becomes a fixed point. For this discrete dynamical system. Okay, but that's the tool. That's a very powerful tool, mapping, passing to mappings in time periodic systems. Very important. Some people think you can do, of course, you can sample any system of multiples of T, and that defines a mapping, but that's a non-autonomous mapping because each and every occurrence of that mapping will give you a different map. Okay, that's very important. So you're not helping yourself with that, right? But if you have a time periodic system, then the evolution rule is time periodic. So it's always the same mapping that takes you from 0 to capital T, capital T to capital 2. It's an autonomous mapping. Okay. What's next? So I spent a lot of time on this, but I hope it was time well spent because it's the most important bifurcation. And I didn't then talk about plus. This is called, I got carried away with this. This is called a supercritical bifurcation because it happens over the critical value. Actually, I should add that when I say the fold bifurcation. I'll just add that here, supercritical, because you hear that term a lot. That's due to the minus sign that I have picked. If I pick the plus sign, then just invert this whole diagram. And then, so your system head, that's the property of the system, okay? And because you just happen to have a negative sign there, then the diagram becomes that, and we call it subcritical because it happens below the critical value of the parameter. So if you allow me, I'll just grab this if I can and move it slightly and squeeze that information in there. So if I say plus sign, that's subcritical. And I'm not going to draw that curve because you would be able to do that. Just imagine that you're swapping the sign and that this whole structure will be on the other side. So what you will then observe locally is that two equilibria get closer and closer to each other and merge, and after that they disappear. So if you think of the forcing frequency here in terms of the parameter, bifurcation parameter, which it is locally, right? Then what you have here is a subcritical fold, and what you have here is a supercritical fold, right? I'm pushing somewhere the keyboard. So supercritical, and what you see here is a subcritical. No, the other way around. Because the bifurcation happens sub relative to the increase of the parameter. Okay. Yeah, I'll see any questions, but any chats? Oh yeah. Regarding bifurcation diagram, do the vertical lines correspond to different sections at u equals constant for a C+1 manifold like the one we drew when we studied the center manifolds depending on some parameters? Exactly. So this is a bifurcation diagram. And we basically, the center manifold in general is of course a curved object, but I can I can imagine the center manifold as a graph over a one-dimensional variable, which is x. So I can just project the dynamics onto x. And then in the x phase space, these are just individual phase spaces that you get for that particular value of the parameter. Right? So what I'm showing here, look at this curve. What that means is an individual one-dimensional phase space for a map in that case, right? So the dynamical system is non-autonomous at this point, okay? So we didn't talk about non-autonomous center and unstable manifolds. So just imagine that I have already passed to a Poincare map, a time t map. It is a one-dimensional stable manifold on which you evolve the same way as you would for a continuous dynamical system, but instead of flowing, you're hopping, right? So an actual the way to think about this is that if I draw this curve, let me draw this up, blow this up, think of this as a one-dimensional phase space for a map, right? Then it has one stable state here, it has another stable state there for that particular value of the forcing, right? Because if I increase the forcing, that's actually a different dynamical system then, because I'm actually changing the right-hand side of the underlying ODE. So what's relevant here for a given value of forcing at a given one-dimensional dynamical system, that this is a fixed point for the map, this is another stable fixed point for a map, for the same map, and this is an unstable fixed point for a map. So if I then start general solutions of the dynamical system and start sampling them, say from this initial condition, then what I'll be seeing is that after one iteration of the Poincare map, I get further up and then further up and converge to that. Likewise, if I start, say here, further down here, let me draw another line, right? So this start near the red one, but on the upper side, then after one iteration of the Poincare map, I jump here, and I jump there, and I converge to the blue curve. If I start high up here, and after one iteration of the map, I start coming down and then coming down. So pretty much the same one-dimensional phase space that we had for dynamical systems, but the evolution is discrete. It's not, it's hops rather than flows. But other than that, the theory is very similar. Like I said, the only thing for a map is just, instead of watching out for dynamical systems, interesting things happen when the linearized dynamics has eigenvalues here, right? But for a map, interesting things happen when the linearized part for the map now has eigenvalues in the unit circle, because that's what it means for a map not to grow. For ODE, what it means not, what implies no growth is that the real part of the eigenvalue is zero, because always the real part that governs growth, the imaginary part of an eigenvalue, if any, it governs oscillations, but not growth. Right? For a map, it's this. But other than that, so what you look for a map is that, do I have any actual eigenvalues here? And the simplest case that gives you a one-dimensional center manifold is being here. You have one, because every term. The others are actually, they are still critical. It's a non-hyperbolic fixed point for the map, but this is the one we're talking about currently. Okay. Next one. So this is the first, the simplest case. And the next case is not, I still want to do Codimension-one bifurcations. It turns out that if I start adding more zeros here, as a high level of degeneracy, that increases the codimension of the bifurcation. However, I can keep the original assumption that I have a single zero eigenvalue here and add further degeneracy, or in other words, symmetry assumptions for the system, which are actually still, many of them are still quite physical. They happen a lot because engineered structures are symmetric rather than natural structures, which tend to be asymmetric, right? So that my next step would be, next Codimension-one bifurcation still turns out to be Codimension-one, is the single zero eigenvalue plus the origin remains a fixed point. Now, because, you know, this is how my structure is engineered to be. I want the origin to be a fixed point because I want the origin I have an intended role for the origin. Simplest example, I have a pendulum, right? I can do a lot of things with the pendulum, start tinkering with all its parameters. As long as it's a pendulum, right? There's a lot. I can change the length, I can change the mass, I can change individual details. I can even think of what else. I can change the bearings, I can introduce various nonlinear damping effects and everything. But the upside down position, the origins, the pendulum is still an equilibrium point, right? Because that's how I engineered it fundamentally. So there are many structures like that. So we have to contend with the case that it remains a fixed point. Now, why is it not covered by what I've already done? Well, look at the normal form. This normal form doesn't know that. Not only do you lose the equilibrium in one direction, but you move the equilibrium away from zero in the other direction, the stable one. So this is actually very relevant for things like the climate, biological systems, or even these systems, right? Where the minute you oscillate in a system, it doesn't matter whether forcing a system, whether x equals 0 was an equilibrium point before or not, because in the force system, you're away from that anyway, right? So, and you're not going to stay there because you're forcing the system from the outside. So there's a number of systems in which that's great, but some other systems, it's not. And I'll give you an example right after this, right after we discussed. And you will find that indeed that's an engineering problem in which I must assume that the origin remains a fixed point. I don't know if I get to the end of that, probably not, but at least set up the assumptions. So again, I have an n-dimensional system. Mu is a p-dimensional parameter, okay? And I again assume that I have a fixed point at 0. So that's one of my assumptions. Again, I assume that the spectrum of the Jacobian, the linearization, when I take the derivative with respect to y at that point, is such that the dimension of the center subspace is 1 precisely, okay? So these are my assumptions so far. So far, they're identical to the case that I've already looked at. Okay, but now comes the additional assumption, is that I want to enforce this condition that no matter what I do with mu, at least for nearby values of mu, when I plug in that value of mu, the right-hand side still vanishes at 0. Which was not the case, and it's definitely not the case under the saddle node bifurcation. But I want to look at this constraint. And well, if that's the case for all mu such that, at least mu minus mu naught is small, so for a continuous set of mu values nearby, well, if that's the case, then I'll just differentiate this with respect to mu, and then I set mu equal to 0 again. Except that I've already at some point declared that my mu naught is 0. So I'm going to keep that. See, so I differentiate this identity and set mu equal to 0, and that gives me the derivative with respect to mu. This is now another derivative matrix, but now with respect to the parameters evaluated at criticality must actually vanish, right? Because I can take this as an identity and differentiate both sides. And I just, since, it's going to be true in some small neighborhood near mu, so I better just, it's certainly true when I set mu equal to 0. So this is my additional assumption, which is new. And that what that is, it's an additional degeneracy. But it turns out it's not serious enough, okay? So it's not going to upset the whole analysis. And that, of course, you would not necessarily anticipate, because, what we could argue at this point, if I scroll back here, is that I just have added another surface like this, right? So I'm now in a situation like this. So at least I need at least a Codimension-2 unfolding, universal unfolding. So I need at least two parameters. That luckily turns out not to be the case. So this is not such a major, it's more of a symmetry, but not real degeneracy. I'll draw a picture in a second as to how to interpret this, but let me actually give you why it's not such a, or the result, or the consequence of the fact that this is not, luckily it's not such a big deal. The universal unfold, for universal unfolding, I can still just pick a one-dimensional system. And that would be, in this case, again, you reduce it down to a one-dimensional center manifold. On that, you pick some parameter, which is general enough, and you will again have the plus minus, but note that I have simply added an X here, which is kind of the easiest way to fix the problem, right? If I add an X here, then the value, no matter what value mu tilde takes, X equals 0 is still an equilibrium point. Or another way to kind of factor this out is X times mu tilde plus minus X. And again, I've already explained the plus minus to you, right? So that should be an explanation for that. This is the universal unfolding. Okay, and again, this is X is from R, and mu tilde is also from R. So what in hindsight actually happens here is that you had a bifurcation surface here in the space of dynamical systems. So in the space of dynamical systems, you did have this, one bifurcation surface, which was already responsible for what we had in the case of the saddle node. And this constraint represents, just very pictorially at the hand waving level, this represents another surface on which systems live with that property. And I'm interested in cases where both properties, namely, what was the bifurcation surface? That you have a single eigenvalue, zero eigenvalue in your spectrum. The second surface says that you have X equals 0 is a fixed point. All the systems, again, this is hand waving sort of pictorially, right? This is taking place in infinite dimensions, but your system is somewhere here. And the way to read this is that, you know what, I still get away with a lower dimensional model, because all I need to do is just explore what happens within the surface here, right? So still a one-dimensional unfolding is enough. Because the minute I said that, in fact, I'm restricting attention to surfaces like this, I'm not leaving that family, then I confine myself to this additional surface. And within this additional surface, I'm crossing the point. So that kind of universal unfolding we were talking about before, in this particular context, doesn't make sense because I have actually imposed a constraint that keeps me on this surface. So this will be irrelevant. I would never get to those domains that the universal unfolding. Why would that be relevant? If accidentally, locally, my system would be preserving the X equals 0 equilibrium point, but there would be no constraint once I'm moving away from it, right? But here I have imposed that constraint for all values of this, right? So that's why I'm getting away with this unfolding. So next time I'm going to explore this unfolding in more detail. We're going to have, and then I'm not going to talk that much about physical meaning because I've done this I'll mention the applications, and maybe we'll be able to finish Codimension-one bifurcations next time. Any typed questions? Sorry again about the audio. I'll just contact IT, not ID. I have no idea what's wrong again. It was working last night already. No questions, no typed questions. Again, my apologies for the audio. You can, of course, if you have questions that you would rather ask in words, then there's always the office hour on Friday, and Balint would be able to answer those. Thank you and have a good day. See you next week.